Okay, let's get started. Just a quick word on the weather, what the weather's doing. So, have a look at this Veta.de website. And you see low pressure in the North Atlantic again. And what that's doing is it's bringing cooler air, I should say, down from the north and wrapping it round. And over the weekend that led to some showers. Now the reason why I guess we've had the odd shower is because of the cold air aloft, and this time of year the sea is still holding on to a bit of heat. So when that heat gets conducted to the air in the lowest few layers, it creates a convectively unstable situation, because the air below is warmer than the air aloft, or the potential temperature below is higher than the potential temperature aloft, and that creates a convectively unstable situation. Did Greg talk about convective stability and instability? So yeah, okay. So that's basically what's happening. As we move on into the week, then what you'll see is this high pressure starts to build, and it builds such that, well, as you see, it moves further to the east, such that it starts to bring air up from the south. So these orange colours, they're warmer air, they're regions of warmer air mass, and you see the UK here. So this is Wednesday, and so we should see it become a little bit more milder as the week goes on. And these high pressure systems, they're notoriously hard to forecast the length of how long they're going to last. So at the moment we're a bit unsure about how long that's going to last, but we think it's going to last into the weekend at least. So you can see here warmer weather over the UK. Now this is still Wednesday, and this is forecast to last maybe into the weekend. So you can see it's still starting to build. We've got low pressure in the North Atlantic, high pressure to the east of that, and that's bringing up this warm air from the south. So hopefully it should be a bit nicer towards the end of the week. Just something else to point out, if we look at the radio sondes again, and I'm going to look at a radio sonde in the southwest of the UK this morning. What you can see is, do you remember last week I showed you some of these radio sonde ascents, and they showed a very sharp inversion? Do you remember that? So very sharp temperature inversion. It means that we had a layer of fairly constant potential temperature, and then we got to the top of the boundary layer where the temperature changed quite markedly. It increased quite markedly. That's known as the temperature inversion. So this week in the southwest, we're not seeing that. We're seeing actually a region of air above the boundary layer that's convectively neutral. It's neutral. What does that mean? Well, we can say it's convectively neutral when the lapse rate is equal to the moist adiabatic lapse rate. And what we should see as the day goes on is that the air in the lower few layers will start to warm as the sun comes out, and so this air will become unstable because the temperature in the lower few layers becomes warmer, the potential temperature becomes warmer than the air aloft. So we should start to see a few more showers, and indeed I think around about 10 o'clock today the Met Office are forecasting showers over Manchester. But that should be fairly short-lived, and then the showers should stop. Try and say that with a mouthful. So that's kind of like the current situation. So we'll see how accurate that is as the week goes on. Last week, recap, so first lectures from me last week. So we did the cloud chamber example, so thinking about how clouds form. And on Tuesday we talked about aerosol particles, and we derived Kelvin's law for the saturation vapor pressure over an aerosol particle. Okay, so Kelvin's law basically explained why not all aerosols act as cloud condensation nuclei, and that's because the smaller the particle, the higher the supersaturation is needed for them to grow into cloud drops. Remember that? Okay, so that's law of Kelvin. And today I want to talk about why and how cloud droplets grow. They form and grow. So we need to consider a bit more physics. What are the molecules around the droplet doing in order for these droplets to grow? And how fast do they grow according to these processes? Because that's important for how we describe clouds and cloud formation processes. Okay, so I'm just going to skip past some of this. So we need to consider some laws. We need to consider Fourier's law for the transfer of heat and Fick's law for the transfer of heat. And also, we're not going to consider Gauss today, that comes in a couple of weeks' time, but we're going to consider a contribution from Maxwell, so famous physicist there, on how he combined these laws of heat transfer and material transfer to tell us something about cloud formation processes. Alright, so first of all, these are observations associated with a nimbostratus cloud, so a fairly deep cloud, which was associated with a warm front. So Greg will have talked about warm fronts. It's a vertically pointing, the top plot here, it's a vertically pointing radar plot. So it's a radar that looks up into the atmosphere and looks at the strength of the echo returns from cloud targets. So the strength of the scattered signal is measured. And what you can see is, so as a function of height and time, it enables you to map out the cloud. And you can see in the first 1500 metres, you see slightly brighter targets, more scattering occurring in the first 1500 metres. So it's a very deep cloud, there's rain falling out of this cloud. So why is that? Why do we have this marked change in the amount of reflectivity measured by radar? That's something to think about. And another plot down here is the Doppler velocity. So you all know about the Doppler effect. So this is the Doppler velocity measured with the radar. And again, we see this marked change in Doppler velocity at about 1500 metres. Okay, so look at the values here. This is Doppler velocity in metres per second. So you see practically about 0 meters per second, maybe -1 meters per second above this 1500 meters level, and then below that about -6, -8 meters per second. What do you think's happening there? What do you think's happening? Why does the Doppler velocity suddenly change from being -1 or so to about -6? Any ideas? What do you think? What could explain those observations? Someone say anything? Anyone want to have a guess? Feel free to speak up. No? It is early on a Monday. Yeah. What do you think? Do you genuinely have no idea? You have some ideas, but a bit afraid to say. Shall I tell you? I think I'm going to have to tell you. Right, so above the boundary layer, temperature decreases with height. It's cold. So there's ice. There's ice in the clouds. Now, snowflakes fall with about a fall speed, terminal fall velocity of about -1 meters per second. Raindrops fall much faster. So basically, what's happening is the rain's forming when it crosses through this layer. So the raindrops melt at 0 degrees Celsius, sorry, the ice crystals melt and form raindrops at 0 degrees Celsius. And then they start to fall and we get rain. So much of the rainfall in this nimbostratus cloud formed via the ice phase. So it was ice before it was rain. And the reason why we got rain on the ground is because when we had ice in the cloud, the ice was able to grow to large enough sizes that it was able to fall through the atmosphere and fall through this melting layer and then melt and fall as rain. Does that make sense? So we're going to start to consider the pathways by which we get rainfall in clouds. And we're going to start first, not with the ice phase, but with the liquid phase. That's what I'm going to talk about today. So these are some more observations. I showed you some observations last week. Now these are observations, different observations inside clouds taken with an aircraft. And they're histograms of the sizes of cloud droplets, or even rain droplets, liquid droplets. So what we can see, this is the number, it's the number per diameter bin width. You've all seen histograms plotted this way, yeah? Against the size in micrometers, the diameter in micrometers. And something to the different colours are just different instruments that measure the same thing. So they all tend to agree. They don't always agree, but this is one graph where they agree. So the observation is, I guess, they tend to be distributed in size. They're not just one size. So we've got a fairly broad distribution, from small sizes up to large sizes. Okay, so in this particular case, going up to 300 microns in the cloud, that's 0.3 millimeters, about that, 0.3 millimeters. So these are quite small cloud droplets, okay? Not typically what you'd expect to see the sizes of raindrops on the ground. Okay, the other observation, so we plotted the log of the number against linear size, and roughly speaking, in certain parts of the distribution we can draw a straight line. So we could represent this data with an exponential, a negative exponential. Does that make sense? Because if it's log against linear, log linear space, that means it could be an exponential, e to the minus something times diameter. Okay? So the important observation there is the observations tell us that the droplets in a cloud are not just one size, but they're distributed in size. That's going to be important later on when we start to consider some of the theories. So yeah, negative exponential can describe the data reasonably well. I'm going to skip past this bit. So we're going to start to consider how droplets grow from water vapour. Before now, we just considered the thermodynamics of how that happens. We considered thermodynamic equilibrium. But we actually need to consider the movement of molecules. What causes the movement of water vapour molecules towards the drop before they can condense? Okay? And when they do condense, that releases latent heat at the drop surface, which must be radiated away or conducted away into the air. So we start with Fourier, and the physicists will have learned about Fourier. And in 1922 he presented his work, and this was the basic equation. Have you all seen this before? Anyone not seen this before? So the current density of heat, watts per, let me think, joules per metre squared per second, so watt per metre squared, and that's a vector, is equal to basically minus the gradient of temperature. So this is the gradient operator. Okay, and there's a constant proportionality there, the thermal conductivity. So that's what Fourier found. I'm going to use this law to consider how droplets grow. Fourier, as with a lot of scientists of this era, he was a bit of an oddball, and he believed that wrapping himself up in blankets and keeping himself warm was key to good health. And it's quite ironic that this was his downfall. So he was wrapped up and started to walk down the stairs, and because he was wrapped up so tight, he slipped and fell down the stairs and killed himself, broke his neck. So that's a little bit of trivia about Fourier there. So yeah, watch out. So what does that equation do? Basically, if you've got a gradient in heat, it smooths that gradient out. So that's just an observation. If you start with a condition where there's a gradient in heat, the heat gets transferred from warm to cold. You know about that? Very similar, we need to consider the diffusion of mass as well. So, what is this? So, if we're considering the movement of water molecules towards a drop, we need to consider how those molecules move towards a drop. And it turns out the relevant equation is the equation proposed by Fick. Everyone seen this before? Anyone not seen this before? Maybe you've not seen this before. It's the same equation as Neil said that wrong, as Fourier's law. This is Fick's law, okay. Current density, so this is another vector, J. Current density of mass, now this is kilograms per metre squared per second. It's like a flux. And that's equal to minus the gradient of rho, where rho is the density of the mass. So if we're thinking about water vapour, it's the mass of water vapour in a volume, kilograms per metre cubed, you could say. And there's this constant proportionality, D. So this was just a bit after Fourier, and indeed Fick borrowed the ideas from Fourier. So he used Fourier's ideas to derive this law of the diffusion of mass. So what does diffusion do? Again, same as heat transfer, it smooths out gradients. So we've got a gradient in mass, over time that will get smoothed out. So basically the same thing, same equation, similar sort of thing. Okay, now I just want to use those equations to derive something, so we'll go to the visualizer. Hopefully. Okay. So we've got Fourier's law, current density of heat minus K grad T and we've got Fick's law, current density of mass, which is a vector, minus D grad rho. Very similar. Okay. Are you familiar with continuity equations? Does everyone know what a continuity equation is? Looks something like this for mass. So we have the rate of change of rho with respect to time plus the divergence of some current density of mass equals 0. You familiar with that? Okay, so if you're not familiar with that, you don't need to know about that for the exam. You don't need to know about where it comes from. But if you're interested, then there's some PDF of notes which is on this week's lecture notes on my webpage, and you can see where that comes from. So I spend a bit of time deriving that. So if we substitute equation 2 into equation 3, this continuity equation, then we just end up with the rate of change of vapor density. I'll give it a little subscript V so we know we're talking about vapor, equals minus dV del squared rho V, because div dot grad is equivalent to del squared. Div dot grad F is equivalent to del squared F. You seen that before? Have you seen this vector calculus operation before? Yeah, okay. So that is known as Fick's second law of diffusion, and there's an analogous equation for Fourier's law which looks like this: rate of change of temperature, and you end up with a slightly different form, but it's minus the thermal conductivity divided by the density. Now that's the density of the material that's conducting the heat. So we're talking about water droplets. This would be the density of water, of condensed water. So it's not the same as rho V, which is how much water vapour there is per unit volume. Del squared T. They're basically the same two equations. We've got a rate of change of something equal to a minus del squared of that something. Now that's Fourier's second law. So these are the first laws, these are the second laws. Okay. The thermal conductivity, so that's thermal conductivity, is measured in units of watts per Kelvin per metre, for those that are interested. And now I'm going to talk you through what Maxwell did, James Clerk Maxwell, to try to figure out how cloud droplets grow using these two laws. So we combine these two laws to try to figure out how cloud droplets grow. So you need to set up a situation where you've got a sphere. So So this is a cloud drop. That's a sphere, by the way. And we set up a coordinate system with the radius, and so this is consider a drop in a water vapour field, a vapour field, and the drop has mass m. So if the drop's to grow, then the water vapour needs to move towards the drop. And some boundary conditions here. So we can set the water vapour density at the surface of this drop, rho v a. Okay, and remember that's the concentration of water vapour, that's a kilograms per metre cubed at the surface. Now at the surface, by definition, by thermodynamics, let's say it, the water vapour density will be at saturation. So it'll be saturation over that curved surface. We talked about saturation last lecture. So it's the saturation vapour mixing ratio at that surface. So that's our boundary condition. The other boundary condition is at r equals infinity, so some distance far away from the drop, and the water vapour density at that distance far away from the drop is equal to the value at infinity, and that's equal. We can measure that if we measure the relative humidity. That tells us about the water vapour content in the air. Now, why would a molecule move from here to the surface of the drop? Well, it's due to Fick's law. It's due to Fick's law, and we can solve for that using Fick's second law. And the solution turns out to be, again, I'm not going to go through how you solve this PDE, but for those that are interested, it's in the notes, it's in that PDF of notes. So I'm not going to go through how to solve this PDE. But the solution that you end up with for the current density, if you solve J minus dV grad rho, and if you solve for grad in spherical coordinates and del squared in spherical coordinates, you need to write that down to be able to solve this. The solution you find is that the current density is equal to this. It's rho v at infinity minus rho v at a multiplied by, now a, I should say, is the radius of this drop, and divided by r squared. So at any position outside of this drop, the current density can be calculated with this formula. So that's any position outside the drop. Now, if we know what the current density is at the surface of the drop, that tells us what the flux of water vapour molecules is through that surface, through the surface of the drop. And if we integrate that over the surface of the drop, 4 pi r squared, we just integrate that current density over the surface of the drop, that should tell us what the mass growth rate of the drop is. Does that make sense? So we've got the current density on the surface of the drop. When I say current density, that's the mass of water vapour per metre squared per second. And then if I integrate that over all the surface area of the drop, that tells me what the mass growth rate is of this drop in kilograms per second. And the solution we get, so just need to integrate. So the rate of change of mass of the drop is equal to, so there's a 4 pi, there's an A, there's a dV, the diffusion coefficient, and it's rho at infinity minus rho at A. So that's the first part of the problem. So this tells us that the mass growth rate of the drop, due to growth from water vapour, can be described by this equation. It's proportional to the size of the drop, and it's proportional to the difference between the vapour density at infinity and the vapour density at the surface of the drop. So the problem with this equation, we can't really use it because the vapour density at the surface of the drop depends on temperature. It's a function of temperature because it's at saturation, and the saturation vapour mixing ratio, which is what that is essentially, depends on temperature. We talked about the Clausius-Clapeyron last lecture. Warm air holds more water vapour than cold air, so the colder it is, the lower this value will be. So we need another equation to be able to, yeah.
Where's the minus sign gone?
Where's the minus sign? You mean here?
Yeah, that one.
Oh, that should be the other way around. Should that? Hang on, let me see. Minus. Ah, yeah. So, so R's measured out. In order for the drop to grow, vapour needs to come in this way. So that's where the minus sign is. That makes sense. Yep. So the other thing we can consider, similar sort of thing, but the transfer of heat away from the drop, and we use Fourier's law for that. So I'm just going to write down the solution for the transfer of heat. So I'll call the heat in the drop Q, dQ by dt, and because the equations are pretty much the same, the solution looks the same, surprise surprise, except there's a K instead of a D, and there's a T infinity minus TA, where TA is this T, is the temperature at the surface of the drop. So that's Fourier's law. Now Maxwell was able to combine these two equations. So they're basically two simultaneous equations with two unknowns, and he was able to combine them, but you have to make some approximations. Now, I'm not going to go through what all those approximations are, but if you're interested, you don't need to know it for the exam. If you're interested, it's in that PDF of notes. So it's got the full derivation online in the notes. Well, I'll just write down the solution. So the solution is, so after various approximations, which is what Maxwell did, the final equation, dm by dt, is equal to 4, there's still a 4 pi a. There's a saturation ratio, minus 1. So the saturation over a liquid surface, minus 1, that's the supersaturation, remember. And there's a bunch of constants, quasi-constants, which I'll call a function that depends on temperature and pressure in the denominator. We don't need to know the full form. It turns out to be, you know, this is quite a long sort of, yeah, it's quite a long expression involving temperature and pressure. We don't need to know that. We just need to know that the rate of change of the droplet mass is proportional to A and is proportional to the supersaturation. So SL, remember, just so we're become more familiar with these terms, it's the vapor pressure divided by the saturation vapor pressure, which depends on temperature, and big S is the supersaturation, which is SL minus 1. That's big S. So if SL is positive, the droplet grows. If SL, that's big SL, is negative, the droplet's going to evaporate. So we're nearly there. So what I want to do next is relate this to the real world, which is the important thing. So this is the thing you need to take notice of. So we've got this equation that explains the mass growth rate of droplets in a cloud. I want to look at, so my measurements, the measurements that I showed you, it was a size distribution, which was number of particles against size. So we want to use this equation to say something about the size of droplets in clouds. So we can make a change of variable. If we consider the mass of a spherical drop, this is fairly straightforward calculus. So the mass is just 4/3 pi a cubed times the density of water. Yeah, that's fairly straightforward. Then the rate of change of mass, if I just take a change of variable, so if I calculate dm by dt of this function, I'll end up with 4 pi a squared. So I'm using implicit differentiation here. dA by dt. So when I differentiate the a cubed, I get 3a squared dA by dt by implicit differentiation. And then substitute dm by dt into here, and you'll end up with an expression for the rate of change of the radius, dA by dt, which is equal to, we've got the supersaturation, which is SL minus 1, divided by, and there's density of water, there's A, and there's this thermodynamic constant, which I'm calling alpha, which is a function that depends on temperature and pressure. Okay, so all that is just a change of variable. It's fairly straightforward. I've just got this different differential equation. As physicists, I know that you'll have no problem in solving this equation. For A versus time, treats everything else as a constant. And the solution, so I'm just going to write down the solution. I'm not going to integrate, I'm not going to solve this by separation of variables and integrating both sides, because I know that should be fairly straightforward. So the solution is A as a function of time is equal to the square root of A0, which is the initial radius, squared, plus 2 rho alpha, this function to the minus 1, and SL minus 1 T. So that's the solution for how a droplet grows at a constant supersaturation in a cloud. So you can treat these numbers in front of time, treat those as constants in this expression. So why have I bothered doing that? Why have I bothered doing that? Okay, we can use this form of how a droplet grows in a cloud to say something about how it represents reality. And that's what we're going to do now. So I mean, in an exam, you wouldn't be expected to derive this equation using Fourier's and Fick's laws. You might be expected to do the change of variable, and you might be expected to solve this differential equation. It should be fairly straightforward. And then the important part, another important part, is what it means. So So we want to talk about what this means for reality. So let's say that the form of my solution, AT, is equal to the square root of A0 squared plus, I'm going to call this bunch of constants one constant, I'll call it A, times time. So that's what my solution looks like. Now I'm going to say, let's say we look at a graph of how droplet sizes change with time. So the x-axis is time and the y-axis is the size of the droplets, the radius of the droplets. Let's say I start with an initial size A0 for cloud droplet 1, and let's say I start with an initial size A0 for cloud droplet 2. So I'm going to consider how two droplets grow in this cloud with time. So let's say that A0, 1, equals 1. Doesn't matter what the units are for this. We're just considering how particles grow with time. Let's say that my constant, so we're going to consider after a time t what happens to the size of these droplets. So let's say A times t is equal to 80. Doesn't matter what the units are. So then I've got 1 squared plus 80, that's 81, take the square root, means that A final for droplet 1, or A at time, well, where AT is equal to 80, is equal to 9. It's just the square root of 81. Do the same for the second drop. So A0, 2, I'm going to say is equal to 8. AT is still equal to 80 because that's constant at time whatever t is. And so A final for drop 2, so we've got 80, 8 squared is 64, so 64 plus 80 is 144, take the square root and we'll find that equals 12. So what happens when these two droplets grow is they become closer together in size. So if we look at the difference in size before, we've got 8 minus 1, that's 7 units. If we look at the difference after, we've got 12 minus 9, that's 3 units. So growth by vapor diffusion leads to a narrowing of the droplet size distribution. Is that a problem? Let's think about what that means. Is that a problem? The fact that the droplets, do we observe that droplets get closer together with time in size? Well, the observations that I showed you showed that they were distributed in size. Okay, so that doesn't tally. What about rainfall? When you think about rainfall, what causes droplets to fall with rain? If you look at a cloud, does all of the cloud fall as rain? No, it doesn't, does it? So you've got a cloud and you've got some rain falling out of that cloud. And the reason why those droplets fall as rain is because some of the droplets in the cloud are bigger than others. So when they become large enough that their terminal velocity is enough to exceed the vertical wind, that's when they fall as rain. But if droplets became closer together in size with time, then we might observe that the whole cloud would rain at the same time. All of the droplets would fall at the same time. We don't see that. So that's another reason why this process can't explain why we get precipitation. It can't explain the rain forming process. That's another thing. Finally, let's do a numerical example. So yeah, for the exam, I want you to be able to explain why growth from the vapour cannot explain rain formation. The growth in the vapour for liquid particles cannot explain rain formation. And one of the reasons, because it causes this narrowing of the distribution. I'd expect you to show this quantitatively, so you should be able to do this example and draw it on a graph. And then another example, another reason why, is if we say if A0 equals 5 micrometers, let's say we start with a particle size of 5 micrometers, which is the typical size of a droplet at the point of nucleation, which is 5 times 10 to the minus 6 meters. And I'm going to say that the saturation ratio is about 1.02. If you remember last lecture I said that in the atmosphere the supersaturation never really exceeds about 2%. So this is probably a maximum value you'd expect to see of the saturation ratio. I'll just give you the value of rho times alpha to the minus 1, and I've calculated this for you. I wouldn't expect you to calculate this yourself in an exam because it's quite a long expression, it's just putting numbers into a function. But that value is 8 times 10 to the minus 11, and I think the units are meters squared per second, but you don't need to know what the units are, just treat them as SI units. And rho of water is 1,000 kilograms per meter cubed. Now we can ask the question, so typical raindrops, you know, they're about this big. I'm going to say a typical raindrop, and this is on the small size actually, but maybe the size a particle needs to be to start falling outside a cloud. So we'll say, how long does it take to grow a 5 micron particle to a size of 1 millimeter, which is 1 times 10 to the minus 3 meters. So this is a really small drizzle drop. You know, you'd see them much larger than that in the atmosphere. And so if you substitute into this equation and rearrange for t, it will tell you, actually this equation, rearrange for t, it will tell you how long it would take for that to happen. So the solution would be a at time t squared minus a0 squared divided by, and it's a 2 rho w alpha SL to the minus 1. That's the solution. And it works out to be approximately 3 times 10 to the 5 seconds, which is about 3 to 4 days if you work it out. That's 3 to 4 days. Now the problem with that is clouds don't last that long. Okay, so a typical cloud might last of the order half an hour to an hour, maybe a little bit longer, but it does not last 3 to 4 days. So this is another reason why growth from the vapour can't explain the rain formation process, because clouds do rain. Does that make sense? Okay, that's pretty much everything, but I just want to summarise now before we finish. So let me just go back to the presentation. That's Maxwell. Oh, it's not on. Maxwell, yeah. So the main points: laws of diffusion of heat and mass describe the growth of a droplet from the vapour. You should be able to talk me through why that is, and you should be able to refer back to equations, Fick's and Fourier's law. And supersaturation, I keep saying this word, be familiar with it because I'll say it more and more. Supersaturation of water vapour is required for the droplets to grow. That's just because that relates back to Fick's law. So, you know, molecules move from regions of high vapour content to low vapour content. So supersaturation means you've got high vapour content away from the drop. That's why molecules move towards the drop. And vice versa. So subsaturation is required for the droplet to evaporate. And the growing drop is warmer than its surroundings, typically by about a fraction of a degree. So you might expect it to be warmer. It just sits at a slightly higher temperature. And this does not fully describe the growth of cloud drops in the atmosphere. There are other processes that we'll consider as the lectures go along. Any questions? Okay, I'd like to end it there. Thank you.
All this this means it's from very far distance and a surface.
Yeah. So you've got the surface of the drop. Yeah, so negative direction. So J is negative. Droplets to grow.
I asked you to write a little bit bigger. Yeah, because sometimes I can find the
Subscripts. I'll try and across. Thank you. Cheers.
Yes,